So on Slack, I posted a link to the vector tutorial content. If you could all go and pull that up. We're going to start there. And I think we heard some questions at the end of the Raster tutorial of how do I save the comments I've made inside the notebook, or how can I push this back up to GitHub? So one thing you could do right now is you could click on the fork button and then create a fork of it. You'll see your username here, most likely, and then you can fork it over to your repository. And please, if you're following along, you have trouble, you can use the stickies or raise your hand. There'll be folks coming around to help you out with this. And then what you want to do is grab the Git link from your forked repository. And this will just allow you, at the end of the tutorial, if you want to, you can do git push, and it will push all your changes, all the comments you made up to your fork under your branch. So that's an easy way to start backing that up. Okay, so copy that link. And now we want to, I'm going to have to try to move this here. Move it over there. Let's go to the Jupyter Hub, and we're going to open a terminal. And we're going to do git clone the GitHub, the link to your forked version of the tutorial contents. Everyone good? Sweet. Okay, and once you've cloned that, that tutorial content should show up here on the left. A folder for it, which has the vector tutorial in there. Another thing I'd like to do, so Scott has provisioned this instance on the cloud with a pre-configured Python environment, and he's actually working on setting up an environment file so you can recreate this on your local machine afterwards or during the hack week if you so choose. But two packages that we're missing here for the tutorial are also posted to Slack, and we're going to install those quickly. And they'll install to your default environment, so you'll be good to go. So under Slack, you'll see here in red this message, conda install, yes, from the channel conda forge, map classify, and context type. So let's copy that and paste that into your terminal. And this will install these two packages to your current active environment. So this is a simple way. During the hack week, as you're working on your projects, if you discover a library out there that you'd like to use, you can simply install it like this to your active environment if you want to pull something in that's not part of the default image. Okay, and because we gave it the flag -y, we don't actually have to wait for this to ask us if we would like to install it. We're all going to just let it do its thing. And it actually happened pretty quick, so you can see now it installed those packages to our environment. Everyone following along? Cool. So let's go over to tutorial contents on the left under these folders, and then to vector. And you can see here, Emilio very conveniently actually put an environment YAML file in there, which has all the packages that are used just for the vector tutorial. So you can grab that at any point as well and install the environment on your local machine for it, which will work just for the vector tutorial. A little side note. Okay, and we're going to jump into the notebooks folder. And I don't know if I can make this a little bigger. And we're going to start with the GeoPandas intro. And one quick side note as well. Let's see, did I post this somewhere? We also, I think we did this in past years, but we also have these tutorials and kind of the entire lesson plan listed software carpentry style under the Geohackweek GitHub IO URL. So if you'd ever like to come back to this content and kind of work through it on your own, there's some additional information in here. But we're basically walking through the introductory notebook, the advanced notebook, the OSM accessing and processing notebook, and then we'll look at some HoloViz examples as well in here. And this is another way to kind of, if you prefer to learn like this, you can do this after the hack week, come back to this content and walk through it in this lesson plan style. Okay, does everyone have the intro notebook up? Yeah? Question? Select kernel, okay. Yeah, so if it's asking you to, you can change your kernel here, and you just want to go with the Python 3 notebook, HANA Env notebook, and select that kernel. All right, so it's going to be another whirlwind tour. There was a lot in the raster tutorial, a lot happening. We touched on some of the vector methods in there as well. But hopefully with multiple coats of paint, they'll slowly sink in kind of what we're doing. So we're going to see some of the same usual suspects here as we explore the GeoPandas package, which is built on top of pandas, and also uses Shapely and Matplotlib underneath the hood. Does that mean something to you guys? When I say GeoPandas uses pandas under the hood and Matplotlib and Shapely? More or less, right? So those are all some of the core packages that GeoPandas brings with it. GeoPandas is a high-level library, and underneath it are these other libraries which are worth exploring. NumPy is pretty low level and pretty core to the Python stack. So if you're new to this, I would encourage you, we're not really teaching Python from the ground up this week, but go back and explore NumPy and what it can do. And that will help you understand some of the objects and their properties that are being inherited with it. That's just a statement to keep in mind, but it's worth revisiting. And come ask us if you have more questions about that. Okay, so let's go ahead and execute these cells. And again, you can hold Shift Return to just execute the cells. And we're going to import a couple libraries here. This is a handy little method to check which version of Matplotlib or pandas imported as PD or GeoPandas you're working with. Here we're going to assign the path to our data folder. And I think this, this library here gives it the full system path, which is sometimes, some libraries prefer that, so that's a good way to organize that. So like pandas series, geo series exists within a geo data frame. Every time I'm saying geo something, we're dealing with the GeoPandas library. And a couple of the entities it understands are points, lines, and polygons for multi-point, multi-line, and multi-polygon objects, right? And the properties that come with that, such as coordinate reference systems and various other things. Okay, so let's see. So now we're going to create a geoseries with a list of Shapely points. So we're using the Shapely point function to create points from these longitude and latitude values and store them as a geoseries, which we're calling GS. And again, in Python, you could call this whatever you want. Sometimes a nice thing to do, especially if you're starting off, you don't have to import things as an abbreviated form. You could just import GeoPandas and then do here geopandas.geoseries to, instead of from GeoPandas, import geoseries. And that might help you remember kind of which library you're using to do various operations. Sometimes being more explicit can help in the beginning. Yep. Let's see. Better? Okay, so we've created some points. We can see what type they are. This is also useful, and the length of this object that we just created. Emilio has a lot of great notes on little gotchas in here, so I might gloss over some of this in the interest of time, but it's worth reading that sometimes you run into little issues where you might have to reformat what you're working on to work nicely. Here we're going to assign a coordinate reference system to this GS object that geoseries object that we just created, because by default, this would be empty. Right, so there's nothing in there, it's returning none. Or I can do type. I think it will tell us that this is none type, right? So there's nothing there. But now that we've assigned it to it, it knows it's a dictionary, and it actually is exactly what we told it to do. And this is now a property of this GeoPandas geoseries, and it will know what to do with this EPSG code later on. This should be a bit of a wow moment. I mean, we're just taking this GS object and doing dot plot, and we have a simple plot right there with the X and Y values. And that's pretty convenient, right? So these are some quality of life functions that they've built into pandas. It's actually using matplotlib under the hood, but you don't have to access all those matplotlib handles to just get a quick look at the data. And that's great, right? That's really, really convenient. But as we'll see, you still, because we now know that it's using matplotlib under the hood and all the features of that library, you can still get access to that Swiss Army knife of a plotting library and use all of its properties to modify the plot the way you want. So if we go here, we're again plotting it, and now we're specifying what type of marker we want, the color, marker size, as well as the X and Y limits. And these are using the PLT functions, which is just an abbreviation for the matplotlib pyplot. We imported it as PLT. Okay, so this might all be basic stuff, but I hope it's helpful. I'm taking a step back and I'm going through things a little bit more slowly. So here we're going to assign a, looks like a dictionary and with some labels. Again, Xarray loves labeled data. That's one of the great features of it. But, and Xarray inherits pandas. And now we're going to use GeoPandas to create a geometry object, which if we assign that to the geoseries, it then automatically knew what to do with this dictionary, and it's actually using the shapely point function under the hood to create these vector points. There is another way to create the geometry, which Emilio is listing up here, instead of passing it a dictionary. This is actually how I often do it. It's kind of a handy one-liner to create a list of these objects. Okay, so moving along, let's see. Now we're going to turn it into a pandas data frame, which is a convenient format to work in. And you can see our rows and columns here. And now we're going to turn that data frame into a geodata frame by assigning the geometry to be the geometry object that we created further up here. And we're just giving it that direct function. We could do, we could call this down here geometry equals geometry, since we already created that object up there in memory. But that's now going to create this geodata frame. And again, we can now just plot that, and it knows what to do with the geodata frame. Emilio, did I miss anything here?
No, but I did notice one, this may be a slightly old version of the notebook. I don't know why, because what's on GitHub is up to date.
Oh,
so
you know what? Yeah, that's actually a great point. I forgot I had forked this in the past, so let me just get set up here. Sorry about that.
There wasn't anything different. It was just a comment there that was internal for me that was still there.
Yeah, I totally blanked on that.
And that's a great illustration of how to remove your clone repo and create a new one.
There's nothing worth saying online. Okay. So I had the wrong version. Okay. So let's get going here. Second here, the same content.
Remember to change the kernel to notebook?
I think it should be that by default. It was.
I'm seeing it in the upper right.
Okay, good call.
The one that. Okay. Sorry.
Okay. And we are back up to speed. All right. Sweet. Okay, so let's load some real data. So Emilio's provisioned an oceans.shapefile. This might be a shapefile you've exported from Esri, or you know, created with a different package. A lot of packages can create these shapefiles, and we're going to load that in with GeoPandas, and it just reads this file and it automatically converts it to a GeoPandas data frame, which we previously created manually by hand. So we can see it has some labels, some different IDs, and most importantly, the geometry geoseries, which is what GeoPandas will use to do various operations. It also embedded, already knew what kind of coordinate reference system it is that's embedded in the shapefile metadata. So it loaded that on the fly. We don't have to assign that. And if we now just do a one-liner .plot, we get a global plot of the rough outlines of the oceans of the world. And again, here we could assign fixed size right there in that line to resize the plot, which is quite convenient instead of the usual matplotlib syntax. Okay, we can check out what type of geometry all these different shapefiles in there. We have polygons and multi-polygons. We can get the area just quickly on demand, but a note that these are in native degree units, which is not really intuitive. So you want to convert the coordinate reference system to meters, or to a coordinate reference system that is in meters, but if you want to get more informative metrics. And we can get the bounds for every one of these individual polygons. Another handy function is to get the envelope of each. So this is a box that is specified by these bounds right here. So sometimes you might have a shapefile and you know you want to pull in some raster data that matches up with this shapefile's area. This is how you can get the bounding box and then use the queries we just saw from Scott to get Landsat data inside that bounding box, which matches up with the shapefile data that you're also working with. Okay? So that's quite handy. And these properties like envelope and geometry, they're just part of this oceans object, which we loaded in from the shapefile, this GeoPandas data frame. So it's all quite handy. Another note is if you're ever curious about what's part of something, you always type dot and then hit tab, and it should pull up everything that's part of this. And in this case, it's a pretty high level object, but as you go further down, you want to know what kind of methods are available to you. This is something to explore. Okay, so now we're going to make a selection from the oceans object. Give me all the instances where oceans equals North Pacific Ocean. That's a very handy operation. If you've seen this for the first time, you'll want to select data by some kind of label, and this is how you do it. So essentially, this column, this value, give me that, and please plot it, and it just does that for you. That's super convenient. It will come up again if you're dealing with GeoPandas data frames. Okay, and all right, so now we're going to read in another data set. I think this is an embedded kind of test data set that ships with GeoPandas. natural Earth low-res polygons. So we're going to read those in. We can look at roughly what's in there and check out which coordinate reference system we're in. We can quickly plot it up. We have the whole world here. Pretty handy. We have matplot overlays. Let's see. And we can plot these two together. So we're plotting the oceans object and the world. And it looks like we're plotting the world on top of the oceans. So that's also very little code to do something quite convenient. And then here we're going to end, we're going to make a little bit of a more fancy plot, kind of clean it up. We're going to add a title, set the y, or the y limits here, turn the x-axis off, and create our final plot. Okay, any questions right here? Okay. Good. If there's no question, would you guys like time to explore? Should we continue on? This is all, it's all pretty basic stuff, but I think it's useful to have as a reference. Yeah. Yes. So the question was, how do I add a cell in a Jupyter notebook? And you can just do insert cell below with the plus button. And I bet there's a key command to do it as well. Command A. No, what is it? Just A. Sweet. Thanks, yeah. Let's see. Natural Earth. Emilio, the question was, is there a way to tell which natural Earth data sets are bundled with GeoPandas?
There may be. I don't know what it is, other than the documentation.
Right, so there's going to be the documentation. We could, sorry, go ahead.
Maybe you could do at the help, the Jupyter help on gpd.datasets. It might, if the documentation is good enough, it might even list it.
So sometimes you can take a method like this and just add a question mark at the end. And when I hit Shift Enter, no,
I would do it on just datasets without getPath. I've never tried it, but I bet there's something. Oh, maybe not.
No docstring here.
Yeah, but it's definitely a subset of natural Earth that is available for convenience.
Yeah, but this is sometimes there's a great docstring that will tell you exactly what's in there. In this case, it looks like they didn't put it here. It might be somewhere else.
I'll try to find it in the online documentation and post it.
Oh, nice. Let's see. Cool. So it says these. Did I do that right? It's right here. Okay. Cool. So that's how you can inspect elements and see what else is there. Good question. All right. Let's see. So now we're going to read in from a Postgres database. We're going to import JSON and another package. And we're going to use this db.json file to connect to that database. This contains some information that we need to establish the connection. And this seems to be the syntax for this package to connect to that database. Just to look at what that connection looks like. It looks like these data are hosted on Amazon, and we're using our credentials to connect right there. And this should work for all of you. We're going to use GeoPandas to read from a PostGIS database, and it has that method built right in. And we're using syntax specific to querying this database to get what we're looking for. Okay, so it's reading right there. again, you can check the current reference system of the data that we got back. And we want to be good citizens and close that connection. And now we can inspect the data by just doing .head on the object. And most importantly, over here, we have our geometry column. It's called something else, geom here, but I think that's okay. And now in a single line, we're going to create with legend true. It just pops up the legend, and we have a nice, again, a nice plot. But every time we've loaded data from different sources, and every time it became a GeoPandas object. And so you can then use that same syntax to plot from right there, plot the vector there. Okay, so now we're going to start bringing it together. We're going to select the North Pacific Ocean. And, oh, and there's some additional links to other great resources out there that kind of expand on some of these methods and libraries. And we're going to plot them together. And I think we're selecting some oceans peripheral to land around the world. And here we are now saving that object to a shapefile. So this is one way to save to a file. Another way is if you want, and let's see. So when you create a shapefile, it kind of creates a lot of additional metadata files with it. So another file format to consider is to
Are you looking for like GeoJSON or?
Yeah, GeoJSON.
The to-file method is generic. It's basically, it plugs into Fiona to write to any geospatial format. Shapefile is, it can derive what format to write to based on the file extension. So you just have to tell a driver, in this case, if you want GeoJSON, you add the argument driver equals GeoJSON. And you have at your disposal the full breadth of OGR or GDAL, OGR formats and drivers.
Okay. I think this comes up in another notebook. I don't have the syntax in front of me right here, but there's other file formats that you can save these vectors files in. And you'll just have to check what the exact one is.
Yeah.
I probably shouldn't.
Just about any, this is using OGR under the hood, and it supports just about any geospatial format you can think of, and way more than you've ever heard of or that I've heard of.
Right, which is awesome.
Yeah.
And so you're not just limited to saving files on disk as shapefiles. There's a lot of other cool formats out there that I would recommend to use that are also more open and actually easier to deal with. Cool, so here we're querying a server and we're actually getting a GeoJSON response back. We're using the requests library. This is a standard, pretty core library to the Python ecosystem. If you have URLs out there where you're hosting data files, you can use requests to hit those URLs and pull in data on the fly. We're getting a GeoJSON response back. JSON is a format that's very convenient for passing around smaller amounts of data on the web with a synchronous instantaneous response. And we're exploring some of the metadata about what we got back here in the response. So we see it's a GeoJSON object and what kind of keys are in that dictionary, and then also the length of the features that we got back. And I think these are ocean acidification measurements from shipboard ship surveys around the world. And now we can plot those point observations along with the shapefiles that we have. Again, all with pretty little syntax. And here we're creating a geodata frame from that GeoJSON response and saving it as, again, every time we're going back to a pandas geodata frame. Right, so everything we're pulling in from different sources, we're converting it back to that. And we can look at the very last element in our pandas geodata frame and see all the additional metadata that came back in that GeoJSON response. Does that make sense? We're good? Okay. Good, so that was a quick intro. How am I doing on time? Hour left. All right, so let's go ahead and move on to the advanced GeoPandas example. So we just got an overview of GeoPandas, and again, that's one of the most powerful tools to deal with vector data in the Python ecosystem. It inherits a lot of other libraries that you can use, Matplotlib, Shapely, and use those methods. Here we're going to pull in some watershed data in this notebook from a Postgres database, and we're going to learn how to dissolve those polygons, also do some reprojection, which is very handy, and you'll encounter later. We'll create a little bit more of a fancy map in this exercise, and we'll also do some spatial joining of polygons and points, so you might want to select. So that these are common operations we're used to doing in other GIS systems, but here's how you do it in Python. And then finally, we'll use a polygon to do some raster statistics. So you have a raster data set and you want to do some statistics about what's happening inside that polygon, and all common methods that you'll encounter in day-to-day work. And so we're importing the packages here, checking the versions of what we have. We already did this. We installed this additional package that we need under the hood, so you all should be good to go on that. So we can leave that comment out.
Frederick, you have to change the kernel.
Okay, good call.
Yeah, they will all come with my local kernel name.
Yeah. Okay, so if you didn't remember to change the kernel right here to notebook. Okay, so we're going to set the data path. And, oh wait. Let's see. So the data path, we're going to connect to that database again using information in db.json. And now we're going to pull in the watersheds data set. And now this variable has become our GeoPandas data frame. Close the connection, check the coordinate reference system, see the length of what we got back, inspect the first object. These are all common practices you want to do whenever you've loaded something in, right? Just explore your data a bit, see what you're working with, if everything is there that you need. And now we can just do dot plot. Which column do we want to plot? A specific type of color map is being specified here, and it's doing it categorically, so we see all these different watersheds for Western Russia. And I think these are multi-polygons, so we can see a lot of different things going on inside each larger watershed. Let's see,
Can I
yeah,
just add something brief to minimize confusion? This data set, hydrobasing, it's ultimately a global data set of watersheds, and it's hierarchical. It has the smallest watersheds are the units that you're seeing in faint boundaries within the solid colors, but it has a coding system, this facetter coding system that allows you to, that is hierarchical, and it allows you to aggregate from building up from the smaller units to large watersheds. And that's what we're seeing here.
Cool. Any questions? So Emilio, this is a global data set?
It's ultimately a global data set. I think I subsetted it. What I loaded into the PostGIS database is probably subsetted. Oh, North America, you see that NA? Hi, Bas. Right there. That's the North America subset of the data set that's the way it's distributed by continent. So yeah, if people want to play with it for their project, you have all of North America there.
Awesome. Cool. All right, so continuing on, we're going to rename some columns here so that it knows what to pull from. And now we're going to dissolve this into a larger watershed and reproject the object. So which columns do we want to dissolve? We're selecting those. And that went quite quickly. And if we look at it, now we have just these larger dissolved areas. So again, a common operation you might want to do. Sometimes it's not able to, a GeoPandas data frame can store objects, geoseries that are of a different type, so it can store points and polygons together, and it can't really dissolve a point, so it won't be able to do that. But I think it just walks over that without an issue. But it's something to be aware of if you are storing different types in the same GeoPandas data frame. Okay, so here we're going to reproject this data frame to a different coordinate reference system, a different EPSG code. And this is an operation you'll probably have to do quite frequently. So various data sets oftentimes come in different coordinate reference systems. So this is a very handy method that I would pay attention to, hint, hint, related. And it's quite convenient. So it's a simple one-liner, 2 CRS, and you get the EPSG code, and now you have that same GeoPandas data frame projected in a different coordinate reference system. Now we can plot it again, and you can see that the shape has changed. Okay, let's see here. Now we're getting the area in square miles. And by performing a simple operation, so this is another thing. Before we ran this cell, this only had these first 3 columns, but here's how you can add a new column to your GeoPandas data frame and tell it what you want to store in that column. So we're dividing the area, the geometry area, by a certain number to get that area in square miles. And so this is how you add a new column to your GeoPandas data frame and do that quickly on the fly. Very handy. It could be any type of computation. And the same goes, so you learn this syntax, well, you're also learning the syntax for X-array and BASC, right? These same ways of doing things are inherited in those even higher level libraries. And here finally we're creating a nice map with a legend with just a little bit of code, but again, we can use some matplotlib syntax to get access to a couple more handles to make a nicer figure under the hood. But the geo data frame object just needs the dot plot operation right there. Okay, I'm going to keep moving here because there's more content to cover. We're going to look at interactive maps with Folium. It's a very handy tool. I think we saw some of that in Scott's tutorial. Again, we're going to explore the head of this data frame, and now we're going to create a Folium map centered around a certain location with a start and zoom. And then to launch that object, you just do map right here. So now inside your Jupyter Notebook, you have a very handy map where you can zoom in and select your different vector data sets. And this was simply done by passing that GeoPandas data frame to Folium, and it knew what to do with it. Okay, it's pretty sweet. Now a spatial join between points and polygons. So we're going to read in a geopackage file. Again, this is a different type of vector data file format that you can save your data in, which is just a single file. Very handy. We're going to inspect the very last element, see what type of data we're dealing with and plot it up. And now we can do, with GeoPandas, a spatial join between the stations that intersect with the polygon data. And we want to get all the stations that are inside of that. And so we get 63 back. And now we can plot those up to see which stations are intersecting with those different watersheds. Okay, and finally, raster stats or zonal statistics using polygons and rasters. Again, this is very handy. So we're going to load a geotiff of precipitation from July with rasterio, which you were introduced to in the previous tutorial bit as well. We're going to open that geotiff. Again, rasterio, just with very simple syntax, makes it easy to quickly plot up your raster and get a sense of what you're dealing with. And now we're going to import raster stats and apply zonal statistics using the watershed polygons and the underlying geotiff. And it's actually going to write out, it looks like it's going to write out a GeoJSON. Or actually not, it's not going to write it out, but it's going to return it as a JSON, which GeoPandas understands, so we can quickly convert that response to a geodata frame. And now we can plot the watersheds that receive the most precipitation around our area, where the raster pixel values were the most intense. So we can see over here in the Olympics, clearly it's raining the most. But really, it doesn't rain that much in Seattle. It's overhead. Around here. Okay, good. Any questions on that? Yes. I wish. So in GeoPandas, it's just so simple to convert the coordinate reference system. With rasters, I usually revert back to Geo. Some of those tools that David was talking about earlier are kind of your Swiss Army knife to quickly redirect rasters. You can do it in Rasterio, but you need to almost manually assign all the metadata pieces when you look at those functions. That said, you can always write a wrapper to just do that. Yeah. When you're doing a spatial join or sometimes it can matter, but generally I would just do it in the order of what you want to layer on top. But usually it knows what you want to do. There are instances, like if you're using, well, we might see this later, but like if you're pulling in a base map and that base map function is pulling the extent to which it should plot, it will do it from the previously plotted element, in which case, like if you plot the points, it might not get it the right extent. So generally, it's good to just keep it in the right order, but oftentimes it doesn't matter. Okay, good. So we're doing well on time here. Please ask questions.
You are actually way ahead of time.
Okay. Were they going too fast?
To this. Oh. No, I'm just saying that you have at least more than I had scheduled.
Good.
So you can dwell on OSM on your own notebook.
Cool. So now we'll move on to pulling in data from OSM using the OSM API application programming interface. And this should be pretty handy for anyone who would like to work with those data. We're going to load a couple packages here, and I actually haven't worked with this OSM MX API yet. Thank you. Thank you. Thank you for paying attention.
And I'll just add that I wrote a summary intro in the software carpentry website, web location on OSM data, because it is not your usual GIS data. That's why having a powerful package like OSMNX is really handy. So if you are confused about OSM or want to learn more, take a look there.
Right, so OSMNX is probably doing you a lot of favors under the hood to get it into something that's more intuitive, or at least intuitive to the Python. Okay, so we're all in this notebook. And it's always good to check your versions here, because sometimes you're working with some version that has an issue and you don't necessarily always want to be on the bleeding edge. So you can always step back a version if you're running into issues that have documented issues already posted to the repo. Okay, so we're just going to start with a bounding box. And again, this could be from anywhere in the world, similar to how we did it in the raster tutorial. So you could specify any area, west, north, east, south, that you want to work with. And I think we're zooming into a smaller area here. And by the way, this is also the Cyclone Kenneth example that you saw in Scott's tutorial. And if you wanted, you could also revisit the tutorial that we had on day one, pull in the bounding box for there, and look at some of the, or check if those buildings you added are available, which they should be. So this is the Cyclone Kenneth AutoSM test deck. And interchange the bounding box for what purpose? Yes. Yep. That's a great question. So I mentioned that a little bit here. And, oh, yes, sure. So the question is, okay, so let's say I don't really know the bounding box and these lat long values, but I have a shapefile, and I know I want to get OSM data for the area that corresponds to the shapefile, or maybe raster data that corresponds to the shapefile. Once you've loaded the shapefile into a GeoPandas data frame, you can get that same bounding box for every single polygon that's in that shapefile. Right, and then just pass that object to the query. So you'll get the coordinates out from right here if you do geometry.bounds, and then you can select that very first one, for example. Right, so it's the bounds, the total bounds of your polygon are a property of that geoseries that you brought in. And if you have questions on how to do that, please come find one of us, find me, and we can work through that quickly. Okay, so here we get our bounding box. And now we're going to use the OSM API, which has been abbreviated to OX, to pull in the footprints, and it has a property to create it as a geodata frame, and we want just the buildings. And in this case, it returns the coordinate reference system as a proj4 string, which is another way to work with with these data. But there were some links earlier to, so there's some very helpful websites out there that explain the codes, and also will list the different formats that you might encounter a coordinate reference system expressed as. So this is a proj4 string, but it could also just be the EPSG code, or any other type of format that you might want to see or use. Okay, so this is how many buildings we got back, and we can quickly just plot them up to get a sense of what they look like on the island. These were hand digitized as part of one of these missing maps campaigns. So they're a direct result of crowdsourced data. We can look at the columns, and this is some of the metadata that can be so important if you're trying to automate your selection of different types of polygons that are coming back. We can see the count, just quickly get a count of the type of buildings that have been classified in this data set. Again, looking at another property, again, getting quick summary statistics. And again, this could be any type of data that you're pulling in. These are methods to quickly get a sense of how much you have of a certain type of feature that you're looking for. And it looks like it's also telling us what type of base imagery it was digitized from. So that's, I think this task, I think this task required Bing imagery, and it looks like most people followed that instruction. And let me just grab my, all right. Okay, so this pays special attention to this cell. It's probably one of my favorite methods. You're using the UTM package right here to, let's look at what these two values are. So it's the bounding box center. Looks like it's the lawn and lat. And it is the UTM package, which we imported up there, will convert these lawn lat values into the appropriate UTM coordinates. Okay. And that's super handy. It also returns the EPSG code from lawn lat values. So if you want things in meters, this is a great way to find out which UTM EPSG code, which zone you're working in, and quickly convert that on the fly. That's a very, very handy function right here that we may come back to. And then again, here in one line, we can convert the coordinate reference system of this GeoPandas data frame to the appropriate UTM zone, and now have something where we can make measurements in meters. Okay. And now area is more informative. It's actually in square meters. So we get a sense of the distribution of the building sizes. For example, there's a histogram of how large these buildings are that were hand digitized. Okay, cool. And Emilio, did you want to say anything about navigating and finding OSM tag types?
The main thing here, compared to what Frederick just showed, is that OSM tends to be or is focused around open streets, originally originated with streets, but human infrastructure, I think it's its strength. But it also has, people have loaded data and it can support data of all types. It could be geological features, rivers, etc. What we did before, if you remember, there was a specific function from OSMNX called footprints. What we're dealing now, we wanted to show how to get other kind of data that is more of natural physical features. I happen to focus on waterways, but the way to get at this type of data from OSM is somewhat different than what we did for footprints. It's a little more convoluted because you have to go dig for the appropriate tags. Again, in my case, rivers are one of my academic interests, so I wanted to focus on that. But if you follow along on some of the links, you'll see that it's not straightforward. The tagging mechanism or the range of tags that exist can be quite varied and overlapping. So you have to be aware of that if you want to be able to pull in data for a particular physical feature and do a little bit of research almost on what the set of relevant tags would be. And that's again, OSM is fantastic because it's crowdsourced, but then again, it's crowdsourced and people tag it manually, and the scheme can be frustrating but powerful.
Okay, so now we're again providing that bounding box, and it looks like this is the tag that we want to get the waterways. And we got 926 responses. We can see the length. We can see these are line string shapely polygon line string shapely objects, and we can quickly plot them. We see that okay, looks like they're in the right place. These look like waterways. It's great. Here it looks like we want the tag for water bodies. And again, I think this is what Emilio was talking about. This is a curious way to specify it, but
yeah, there is no obvious distinction, at least to me, between waterways, which look like rivers, and I imagine they are largely natural rivers, and natural water, which happens to return what looks like lakes or small lakes.
And we can quickly plot them up again. Always verify it's good practice what you're getting back. Now we can put it all together. So here we're plotting the footprints and the waterways, and then also these water bodies all together, pulled in on the fly for any place on Earth through the OSM API. Okay.
And at this point, you could, for example, depending on your workflow, just choose to save it to a file so that you can do follow-up work.
Yeah, so here's a way to pull in training data if you wanted to build a building classifier and have some raster data for that particular. Okay, any questions? Yes. Okay. Maybe one of the instructors can come and.
I couldn't hear the question.
Oh, there is just an error on this cell block. Make sure that text is the same. And if you, this is what I was talking about, if you look at the response without using NumPy syntax to filter this tuple, words right there, but you are essentially using this, I believe, long lat pair to get back your coordinates in UTM, and it's also telling you which zone and zone code is in there. But then you can use NumPy syntax to just get the zone and the zone code, which is what we leave down here.
And sorry, a slight correction. It's not so much NumPy syntax. It's just regular list slices. So basically,
Yes.
it's saying the last two elements.
Yep.
Because
Basic.
for this, yeah, for this we didn't need the UTM coordinates. We just needed the UTM zone, so we can find the EPSG code for the UTM zone.
Okay, cool. So if there's no more questions, I'll move on to the final notebook. All right. So this is a final notebook looking at some of the HoloViz stack. Again, it's a great new library. At the very bottom, there's a link to kind of some of their tutorial content, especially if you're interested in visualizing things on the web and working with large data set. Again, all of the Pangeo ecosystem takes advantage of web-based visualization. So HoloViz was a natural partner to dock onto the Pangeo effort, and a lot of the tools that are in that ecosystem use things from the HoloViz stack. The HoloViz stack has panel, HVplot, HoloViews, GeoViews, which we'll see in a minute, and a lot of other things in there that allow for various different purposes. But this is a great new plotting ecosystem to explore within Python, and gives you some different capabilities than Matplotlib has natively. So we're going to import some of these candidates from the HoloViz stack right here. And here I just collected a number of URLs. These are open base map tile URLs that you can use to just pull in data into your notebook from anywhere in the world. Right? So you can quickly down here switch out the URL that you're using. So choose. Right now we're going to use Google Satellite. We're going to specify a lat long and a distance from that center point that we want to request data from. So here I'm setting the extents like this. And then I'm using GeoViews with the world map tile server and the specific URL that I specified up here, which you could swap out, to pull in tiles of that extent. Then I'm using GeoViews to create an empty points list object, and also initiating the point draw tool, which is part of HoloViews. And then I'm going to pull in that base map and launch it as a little panel inside the notebook. You saw some of these tools earlier. This might look familiar. This is, oops. This is eScience right here. And here I have a tool to digitize the corner coordinates of the eScience building from the top. And the point stream is listening to what I'm doing. And I get those XY coordinates back from the points that I selected on the map. This is a really handy way to just quickly maybe make some annotations on a base map for any place in the world and get maybe some training data in that. And if we look, it's, HoloViz is using a D-frame operation or built-in function here, so we can inspect what did it actually give us back. This is a pandas data frame, so that's great. We already know what we've learned about pandas, so we kind of know what else we can do with this from here. So again, HoloViz is building on top of pandas, or it's at least passing back pandas objects, which you could then convert into GeoPandas objects. So what if I want that base map as that tiled base map as a geotiff? I actually want a TIFF on file so I can use GDAL to maybe do some operations. Here's where we'll use context tiling. And similarly, they pull in from any base map URL. For some reason, context tiling wants the X, Y, and Z to be specified with lowercase. With lowercase syntax. Oops. Yes. Let me just do that.
The kernel, I could see the kernel was the one you have to change.
It's ridiculous. Okay, so just a quick little note here. These are lowercase x's up here. All of this, one's capital. I don't know why, but that's all you have to change if you want to use one of the URLs from the top up there. This is the satellite URL right there. And we can output, I'm just naming the output file output.tiff. You could name it whatever you want. And I'm giving it the same bounding box. So this now will, hold on, I need to run that stuff above. Okay. And that created, again, with the exclamation mark, I can do bash commands, and I can see what's in here, and I can see that there's an output.tiff file right there. And then I can use gdal.info from the command line, essentially, to get the information about that tiff that I got back, right? And so now I have a geotiff on file that corresponds to this exact same area. So this is a great way to just get a base map on disk of any place on Earth. We can use Raster to pull in that, that geotiff and plot it up. So you see we have it right here. And then we can pass those vertices, which I, in this case, did not create. Let's create those again. So now they're here stored in this df object. And then down here, we can plot those on top of the base map that we just loaded in from file. Right? And then we can also convert those corner coordinates to a polygon if we wanted to. And this is my crooked footprint, building footprint polygon. So yeah, those are just some basic operations right there. And let's say you wanted it in UTM. Again, here's where you can use that UTM package. You specify UTM, sorry. Am I using that URL? I don't know if I'm actually using this URL. UTM will convert from lat long, these lat long pairs, and get out those same codes that you saw. You saw the same idea in Emilio's notebook just a second ago. Oh yeah, here I'm using the URL down here. And now I am actually passing that coordinate reference system with the appropriate UTM zone code to GeoViews to pull in the tiles projected in meters. And I'm, again, initiating an empty points object, but I'm assigning the correct coordinate reference system. And CCRS, this was imported from CartoPy, which is working under the hood for GeoViews, and CCRS understands a lot of different projections. You don't have to use UTM if you want to work with something else. And create that point stream and load the panel base map. And now we can see that compared to earlier, you know, the panel base map was in a kind of a more lengthwise shape, and now it's projected with a more equal area. Okay, so select some vertices totally off. That's okay. And here we're getting the coordinates now back in UTM by specifying the projection right there. Here's a similar version of the function you saw. It was a one-liner in Emilio's notebook. Here I wrote it as a function to get the appropriate EPSG code for any given long lat. And now I'm pulling out the EPSG codes, defining an output file name. I'm just making sure that I don't have that on disk, which you wouldn't. And now I'm using GDAL warp to answer your question. It's not just 2CRS. With the raster, here I'm using GDAL warp to reproject that raster file to the UTM EPSG code that I want. I'm using cubic, and a couple of the flags also recommended by David. You need this best practices when creating geotiffs. Right, so this is a one-liner to reproject that GeoTIFF. And now I can open that again with Raster, and if we plot it up, we can see that we have a couple man values here on the side because it's been transformed a bit. Not as dramatic because it's only a small area, but you see that. Okay, so that was a lot. We have about 15 minutes left, and now I'd like to see, maybe we could stop for a second and do an exercise. See if you can reproject and plot the vertices of the in UTM on top of this UTM raster. So if you followed along, you should have all the ingredients you need. With GeoPandas, it's just a simple one line to reproject those points and then plot it on top.